In this video, we're going to talk about recursion. So recursion is when a function calls itself in order to solve whatever problem it's trying to solve. So you can think of recursion with a problem something like factorial, where if we have some math, something like this, n factorial is equal to n times n minus 1 factorial. And then we have a base case where we say 1 factorial is equal to 1. So we use factorial as part of the definition, although eventually we have some base case which stops that recursion. Otherwise, we would just go forever. So we're going to use the Fibonacci sequence for our example. So the Fibonacci sequence is the series of numbers we get when for any, well, actually, let's start off. We'll say Fibonacci of, or the first Fibonacci number is 1. The second Fibonacci is 2, or is 1 as well, And then Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. And that should be equal. So that's the definition of what these are. So let's do this iteratively. And I'm going to use a while loop. So I'm going to call this fib while. It's going to take a parameter. I'm going to define some variables. F is going to be 1. F1 is going to be 1. Let me take the space out just so that it's a little more clear what things are. And F2 is going to be 1. And my loop variable, I'm going to start off at n. And while I is greater than 2, F is going to be F1 plus F2. F2, I'm going to move that to be F1. And F1 is going to be F. And then I decrement my loop variable. So essentially what we're treating this as is this is fib of n minus 1. This is fib of n minus 2. And then as we move through, those get updated. So in the next iteration, fib of n minus 2 will be what was fib minus 1. And this may be confusing, but if you write it down on paper, I think you should be able to tell what's going on there. Essentially, as you move through calculating this, you need to keep track of the two previous numbers. And then once we're done, we'll return F. So let's see how this works just to verify that we get the correct result. Actually, we'll do this in a moment. So let's step a for loop. And for here, we'll set our max as we'll make a symbolic constant, and we'll do 25. So this will give us all the Fibonacci numbers up to 25. So II is undeclared. And I had an extra comma there. And I believe we called this fib while. So now if I run this, so I get the Fibonacci numbers, and I can compare this to, for example, if we look at Wikipedia or somewhere, you can find this sequence, but that sequence is correct. I also don't want to start at 0 because in our definition, we're saying it starts with 1. So let's start from 1. Okay. So now let's try to do this recursively. So recursive function, we're going to return an int. We'll just call this fib. And it'll take an integer parameter. And if n is less than or equal to 1, then we're going to return n. And then otherwise, we're going to return, and here's where we're going to use recursion, fib of n minus 1 plus fib of n minus 2. And there's my function. So you notice it's actually a little simpler, and it looks a lot more like the definition. So here, let me change that. So I'm missing a semicolon there. And it looks like we got the correct values, just as we expected. Okay, now the problem here is that this is horribly inefficient. Just to show you, I'm going to declare a global array, and I'm going to use this to keep track of how many times that recursive method gets called. So if we go down here, and if this gets called with a negative, it's not going to work. So I'm not going to worry too much about checking for that case, because in theory, you should never give it that input. So I'm going to increment counter at n, and I need to initialize the counter. And then I'm going to only call Fibonacci of 25. And then we'll print everything, or we'll print the values of the counter array. And this will tell us how many times we call each function, or how many times we call the function for each input. So here, the Fibonacci of 25 is 75,025. I think we need to make counter a little bit bigger. Yeah, that's better. So you'll see that we get the right value here. That's what we would expect. But notice we call counter 1 Fibonacci of 25 times. Notice that those two numbers are equal. Let me delete this D. And if you'll look, notice we get the Fibonacci sequence of numbers going back from the number we're checking all the way down to 1. And so for each one of those values, we call that function for that value some Fibonacci number of times. So really, we could actually write a function that worked exactly like this, that just counted the number of times Fibonacci of 1 was called and returned that. We wouldn't even need to do any math. We could just set up a counter to count that. Obviously, that's not what we want to do. But it's important to realize that that is how inefficient this is. We don't want to be making this many function calls. Eventually, we're going to run out of memory. So a way to avoid that is using what's called tail recursion. And tail recursion is going to be similar in structure to a while loop, at least conceptually. And it's going to call a helper method. And so this function, fibtail helper, that's where our actual recursion is going to be. It's going to take n, f2, and f1. And actually, I think we're going to need to start fib2. It's, well, let's see. I think we might be okay. So we're going to increment the counter to see how many times we call this. And if n is less than or equal to, I think 2 should be sufficient here, we're going to return f1. Otherwise, we're going to return fibtail helper, n minus 1, f1, and f1 plus f2. And let's call fibtail here instead of fib, and let's see if we get the right answer. We have an implicit definition of fibtail helper. Fibtail helper. Okay, there we go. So you'll notice it returns fib of 25, but which is the correct answer, 75,025. But notice it only calls each input one time, and that's called tail recursion. That's going to be a lot more efficient. So something to keep in mind when it comes to recursion, doing things tail recursively is going to be significantly more efficient than sometimes that naive interpretation where you take the mathematical definition and convert that straight to code. And there's a lot more you can do with recursion. This is just sort of to show you the technique. Again, the while loop is probably the most efficient of all of these. And for some things like for, say, summing a list of numbers, you can do those recursively, but you could also use a closed loop formula. So always use the best tool for the job. The point of this isn't really so that, hey, always try to write recursive functions, but you should be aware of them. They do come into play for a lot of things, especially when it comes to some data structures have a recursive structure to them, that doing or writing your functions recursively they're a lot simpler code than if you tried to write an iterative solution. So I don't think, okay, I didn't label this, so let me, so just to be clear, I'm going to move fibtail ahead. And the reason for that is just because that's really the function that gets called. I don't want to create confusion. So we'll need to add a forward declaration up here. Remember, with forward declarations, we don't actually need the variable name. So I'll take those off here. And let's make sure it still works. And it does. One more thing, let's move the printf to the end so that we don't have to scroll up to see that. Perfect. Okay, so that's a quick introduction to recursion.